The topic of my presentation for the seminar for course AI 60002 is on large-scale hydrological modeling using big data. I am Samarpeta Sarkar and my course roll number is 21GG92W02. To begin with, let's understand the schematic. Let's understand through the schematic diagram the processes behind the hydrological cycle that comes into play. It can be broadly divided into the atmosphere, the surface hydrology, and the groundwater hydrology. So it's pretty elementary science that in the atmosphere, due to the air pressure and temperature differences, precipitation happens, and precipitation mostly in the form of rainfall when it falls on the surface, it gets split into the surface runoff and the subsurface runoff underneath the ground surface. Now, depending upon the various geological and geomorphological factors, which includes the topography, the various geomorphological, that is the form of the landscape, the slope of the terrain, and also the composition wise, what is the composition of the soil and the rock surface, and its relative capacity for infiltration or the non-permeability of the surface to seep in the water determines what proportion of the precipitation is divided into the runoff and the subsurface unit, that is as the in the form of groundwater. Now again, the subsurface units, they also need to be of certain physical, then also need to be of certain physical and chemical property to be what is known as the aquifer unit, which it actually contains the water. On the surface, the various drainage networks carries the surface runoff in the form of rivers or say small seasonal drainage streams. So this altogether again comes on to the surface in various mass exchange relationship between the surface and subsurface water, between the surface and subsurface water. Surface water again in the rivers, in the lakes, and also of course in the wide oceans and sea surfaces gets subjected to the evapotranspiration processes from the water bodies as well as the vegetation, and this completes the cycle and brings back the water back to the atmosphere. So it is more or less a closed loop system with the continuous mass exchange relationship between all these three spheres, and in between the complex maze which a water molecule follows from the atmosphere to the, say, finally discharge into the ocean, takes a very complex path, and it is highly determined by different processes and the meteorology and also the geology as explained by the diagram. If we refer to the this system, it is again very much closed system, when closed system, and the area and extent over which this system mostly happens is what is geologically termed as a river basin. It is the unit of the hydrological cycle in terms of the geological properties of any area. So mostly this entire process which we described here in the left hand diagram, it is again experienced mostly within a water basin, which is divided or separated from another adjacent basins, mostly by some sort of a hydrological divide based on the topography of the region. So as it can be seen here, the precipitation is happening, the surface runoff is in turn flowing downstream and is used by different agricultural system and suburban areas, by industries, and these different anthropogenic units also extracts the groundwater, and subsequently all these discharge goes back to the rivers or bays or sea, wherever the basin is opening up to, or the discharge is happening through the sink point. So In 1987, Keith Bevan took a perspective inspired by Thomas Kuhn's there's the book of a theory of scientific revolution where he defines the paradigm shifting uh, concept in science and in scientific revolution. So Keith Bevan, inspired by this in the at the Symposium of International Association of Hydrological Sciences, he argued that the extension of laboratory scale theory to the catchment scale is unjustified and that a radical change in theoretical structure, a new paradigm, will be required before any major advance can be made in predicting catchment scale rainfall runoff response. So basically, what is being said here, what he said, like Keith Bevan said in 1987, is that whenever we are trying to model a process, we are trying to study it scale up or scale down based upon the laboratory scale inferences. We are trying to upscale it to the catchment scale, but that it is it seemed unjustified at his part, which makes sense because of the heterogeneity which occurs over a catchment scale, and also that the properties of a catchment is very different from the adjacent catchment in itself. The variations in the hydrodynamic property and also the meteorology is so diverse that this extension of upscaling, downscaling, not only from a laboratory scale to catchment scale, but even from a catchment scale to global scale, it is unjustified in justified with respect to hydrological systems. So, for this, he proposed that two things would be necessary to push the field of surface hydrology into a new period of normal science. So, first is the scale relevant theories of watershed. Now, hydrology in the future will require a macro scale theory that deals explicitly with the problems posed by spatial integration of heterogeneous non-linear interacting processes and also the uncertainty quantification. So such a theory will be inherently stochastic and will deal with the value of observations and qualitative knowledge in reducing predictive uncertainty. Why modeling is required? If we are studying a system, we have all the data. So why do we model? Why do we model any system for that matter? So modeling has become an integral part of the decision making process for water engineers and managers. Secondly, recent research in hydrological modeling tries to have a more global approach to the understanding of the behavior of the hydrological system to make better predictions and to face the major challenges in water resource management. In 1985, UNESCO hydrological models have taken over the most important task in solving the problems pertaining to hydrology. So, it is valuable for studying potential impact of changes in land use or climate. The computerized methods to create an understanding of hydrological phenomena are based on various modeling strategies, which simplify a hydrological system to simulate its behavior. So, modeling has taken up over not only hydrology but all spheres of natural sciences, and it's important also because in this fast moving world, the decision makers need a complete understanding of the model, and that varies from empirical model using all the data, the physical processes, and as well as the latest disruptive technologies. So, based on this plethora of options which are available for modeling, which model should be used is also a pressing question when it comes to modeling of any natural sciences, and here in this case, as we are talking about hydrological systems. So, that basically depends on what time scale are we working on, what hydrological quantity are we trying to obtain, what data do we have for that particular watershed, and also how fast computer or processing technology do we have in hand. Based on this, let's just briefly refresh our basic definitions on the various modeling pertaining to hydrology. So hydrological model is a simplification of the real world system. So it may be the surface water, it may be the groundwater, it may be say the relationship between surface water and groundwater, and this modeling helps in the understanding say predictions, the prediction of the hydrological surface water discharge, and this and thus based on this understanding we can manage the resources both say the in a quantitative way and also in a qualitative way. So these informations are very important, especially based on say decisions like in monsoon, if we are expecting, if we are predicting that the monsoon will be higher than usual, or for a particular period of time we are expecting heavier rainfall. So accordingly we need to have preparedness with respect to say reservoir monitoring. So when should be the when should the dam gates be open to let out the excess of the water flow in the dam system, so that there are no catastrophic disaster happening due to the mismanagement. So also for flood prediction, when should the vulnerable people in the floodplains be evacuated, so that no natural disasters occur due to the excessive rainfall and thus flooding. So next as we are saying of conceptual models, they are commonly used to represent the important components, say features, events, and processes that relate hydrologic inputs to outputs. So these components describe the important functions of the system of interest and are often constructed using entities, stores of water, and relationship between these entities. The conceptual model is coupled with scenarios to describe events, so either input or outcome scenarios. Now, lately, the deep learning AI technologies are widely being used, especially for modeling the complex high dimensional data. And this is very successful in inferring a very robust and scalable insight while minimizing the degree to which manual labor is needed. But it is also to be pointed out here that it is a black box method, and the processes which exactly happens while modeling cannot be one to one understood for that matter. So what happens is there are basically three or more layers: the input layer, the output layer, and the hidden layers over which the processing happens through various algorithms, through various activation functions, which are decided based upon the nature of the data structure and the kind of application we are trying to model using the deep learning methods. So DL is basically the subset of ML, and this is a higher level representation of the underlying data sources. And DL is capable of extracting substantial features without being explicitly instructed, and thus is more immune to raw and noisy data. So as I was previously describing that since the same processes are not governing the rate or the hydrological activity from one catchment to another catchment, the extent and intensity of each of the processes vary in different catchments and watersheds. So individually understanding the processes is and then generalizing it is a far-fetched attempt while trying to understand the overall condition using empirical methods, and also that's a very data exhaustive process which in most of the cases are not available. So if in such cases DL is used, as DL does not ponder very much onto the processes which is happening, so it has shown to perform substantially better than other physical and empirical based models. And the various successful cases and the case studies which are available in literature, I'll be briefly summarizing these works in the next. So before that, the different task types which are defined by the output form of a DL network can be classified into six types. The first is regression. So it is a machine learning task that predicts a continuous value Forecasting the next measurement would be an example of regression task. This usually happens like with a label data. If we have the label data and we perform the relation between one dependent and one dependent variable, and we carry out the regression. Classification is when we aim to model to predict whether the sets of input can be categorized into some classes. So the number of classes are not limited here, and predicting whether, so for example, predicting whether the next day will be a dry or wet is a classification task. So not necessarily label, it will form different classification clusters, and based on that we can make the decisions. Third is sequence prediction. So again, regression of a sequence of numeric values or a vector, like the forecasting of the next 24 hours of measurements for say a stream discharge sensor is a sequence prediction task. Matrix prediction is regression of a matrix of numerical values, uh, and each of the values in the predicted matrix would be, say, if we consider the precipitation, then the precipitation of the sub-region within the actual region. So we'll be forecasting for the particular study area. Fifth is unsupervised learning, and it is a learning task where applying competitive learning instead of error correction learning like previous task types. So this decreasing the dimension of a high dimensional hydrological input data to lower dimension visualizable data would be an example of unsupervised learning. And sixth is reinforcement learning, where the output is unspecified, and it works on a reward penalty policy, and like in a try and error mechanism. And an example of this would be when it learns, as I was telling, when to release water from a dam. So we'll go we'll be briefly mention and discuss the different successful case studies of use of deep learning deep learning for large scale hydrological modeling in the domain of subsurface and groundwater study. This also is categorized into different broad application. So the first step is the estimation of the water table level or flow rate. So with the groundwater monitoring wells data, this is like a 1D regression task similar to surface water prediction using recurrent model. So few of the literature while which I came across, which did such kind of work, and the models that they have used were Jong and Park 2019. They applied the NARCS, LSTM, and GRU on the water table level estimation with the observed data from the monitoring wells. It found that the estimations from the NARCS and LSTM models are superior to those of the other models in terms of prediction accuracy. Jeong et al. Again in 2020, he further applied the LSTM with multiple loss functions, which shows that the proposed LSTM model with cost function of MSE with Whittaker smoother, least trimmed squares, and asymmetric weighing has the best performance on groundwater level prediction with data corrupted by outliers and noise. Again, for groundwater flow prediction, Wang et al. 2020b proposed a theory-guided DNN, which only makes the predictions of groundwater flow, but also not only but also the parameters of the PDA, as well as the initial condition and boundary condition of the PDA. It predicts. Now, by constructing the loss function, the theory-guided NN can provide the prediction results with reasonable parameters of the physical model PD. So these were for mostly 1D regression type of studies, but groundwater studies also takes into consideration the cross section and time series and focus on a 2D map, example like groundwater balance map. So time series is recently gaining a lot of importance with respect to the usage of neural network and deep learning for the prediction of the multivariate systems. So, like the dependency of groundwater as well as the other meteorological factors, which are very dynamic compared to the other geological and geomorphological system, which are more or less static compared to these which are compared to the meteorological system. So, Sun et al. 2019 proposed a convolution neural network model using the physical model given by NOAA simulation result as input to predict the groundwater balance. So the CNN model is used to correct the physical model results by learning the spatial and temporal patterns of residuals between grace and NOAA simulations. So results show that the CNN can significantly improve the physical model simulation accuracy. So now this is also a classic example, like all these inputs which were used, they were of different spatial resolution, also spatial and temporal resolution. So CNN significantly improved the accuracy by incorporating these different these different inputs from the simulated data, and also the grace observations, and overall it resulted in a much more stronger and robust model compared to each of them individually. Similarly, some of them focuses on 3D mapping as well. So Santos et al. In 2020 proposed a 3D CNN to predict the estimated state solution of the Navier-Stokes equation for laminar flow, which is the flow rate with 3D rock images. So this 3D CNN is a surrogate model of the Navier-Stokes equation and takes less than a second. So that's really fast computing. So, in groundwater studies, one of the other deep learning application is inversion, such as to identify the contaminate source in groundwater. So, some complex traditional algorithm can be used to solve this problem. However, it will not be efficient when the data is in high dimension. So, when it comes to groundwater or water resource management, not only the quantity but also the quality of the data is imperative, because we want the data to be portable so that it can be used. And due to the increased anthropogenic usage, the shift the change of blue water to green water to gray water, the amount of usable water is decreasing, and the um, management of groundwater resource for both for the present day and for sustainable usage requires that the contaminant source should also be measured. So, Moe et al. 2019b developed a deep autoregressive neural network which was used as a surrogate model of this high dimensional inverse problem and provides more accurate inversion results and predictive uncertainty estimation than physical models. Lalo et al. 2018 proposed another approach for the inversion by using GAN. With the GAN models, the inversion rapidly explores the posterior model distribution of the 2D steady state flow and recovers model realization that fit the data close to the true model results. Sun et al. 2020 investigated three learning based models, namely DNN, multiple linear regression, and SARIMAX, to find missing monthly data in total water from GRACE data. Based on the results, the performance of DNN is slightly better than SARIMAX and significantly better than MLP in most of the basins. So, the three learning based models are reliable for the reconstruction of GRACE data in areas with humid and no low human interventions. Certainly, because the processes which are happening are mostly natural, because as it's in that, in little human intervention, the processes occurs are mostly are not intervened by any of the other drivers, like say water diversion due to candles, and uh, say increased extraction for irrigation or industrial purposes. So these studies show that the deep learning models can work as surrogate models by improving computational efficiency in groundwater dynamic predictions and inversion. So next, coming to the surface water, which is more visible as compared to groundwater, and the observation network is also uh, very dense in some of the important rivers and reservoirs across the globe. So the prediction of water level is crucial for water resource management and protecting the natural environment. So many studies have applied deep learning methods such as LSTM and AN to forecast the water level from one day to 1 year. So, depending upon the prediction, depending upon the necessity of prediction and planning required, both 1 day estimation prediction is also important, and 1 year for future preparedness is also important. So the first study investigated two different ANs, namely LSTM and feed-forward neural network, to forecast the lake water level. The monthly measurements for 38 years of Vrana Lake, Croatia, is utilized for training the models to predict 6 or 12 months ahead of the lake water level. The set of sequences with different lengths created from the obtained data is used in the network instead of using classical lag data. So the results of LSTM and FFNN are compared with classical time forecasting methods and AD. So according to the results, the performance of LSTM is the best among the models in all scenarios, while feed-forward neural network provides better accuracy than the uh, compared methods in both in uh, in both 6 and 12 months prediction. So next, Liu et al. Developed a Bayesian neural network, which is based on AN with posterior inference to forecast the water level in a reservoir to derive operation rules. The results suggest that the current reservoir status and future inflows are the primary factors that affect operational decisions. The influence of inflow uncertainties on reservoir operations is also more than model parameters uncertainty. Their findings show the impact of the input data alongside the promising results of the Bayesian neural network. So, as we can see from the literature, that there is a surge in time series DL applications in a data limited setting. So, though the progress is solid and widely reported superior performance can be observed, there are some challenges and limitations, which are number one, the most significant one is that because the data from a small number of sites are employed for both training and test, there are limited opportunities to train or evaluate the model for extreme conditions, which is necessary for predictions at least. So this can be managed or mitigated by exposing the model to different situation, a myriad of situation in a big data setting. But this is in a data limited scenarios, it is a major constraint. The implication of such limitations should be carefully considered when we are using it for different mission critical application. When the stakes are high, like when any flood forecasting needs to be made, or water in strategic location, this can be a real limitation and challenge. Also, as such a model is entrained in the specific dynamics at a site, and therefore does not need to understand the implications of control factors. These models do not capture the fundamental process as we discussed, and thus cannot be migrated to other regions if the model is not exposed to data from that particular. So to conclude, the features of DL, example like higher accuracy, high efficiency, low cost, and low barriers, are bound to increase the public's access to hydrological prediction. So if better prediction is the sole purpose, DL offers not only highly accurate results but orders of magnitude lower cost in terms of both model preparation, validation, and runtime computation efforts. If understanding the relationship or causes and effect is the priority, then we need to employ more interpretable AI techniques, which are so far rare in geosciences. So that I come to the end of my presentation. Thank you.